Welcome to The Explainer, where we break down some pretty big ideas. And today we're diving into one of the absolute biggest, the P versus NP problem. It's a question that really gets at the heart of what computers can do and what they might never be able to do.
Okay, let's kick things off with a bit of a paradox. We all know computers are just unbelievably fast, right? They can perform trillions of calculations every single second. But, and this is a huge but, there's this entire class of problems out there that are so complex, so monstrously difficult that even the fastest supercomputer you could possibly imagine couldn't solve them. Not in a billion years, not in the entire lifetime of the universe.
All right, take a look at this graph. It shows something pretty fascinating about how problems get harder. See those lines kind of hugging the bottom? Those are the manageable problems, the ones that scale up pretty predictably. But then, look at those lines that just shoot straight up, almost vertically. That is what we call the Great Wall of Computation. Those represent the problems that just become impossibly hard, even if you just make them a tiny bit bigger. So this table really puts that Great Wall into perspective. I mean, look at this. A problem that scales at n squared, that's a piece of cake for any modern computer. But then you look over at that n factorial column. Wow. With an input of just 20, we're talking about 77 years to solve it by just trying every option. Bump that up to 30, and it would take longer than the age of the universe. It's just mind-boggling.
So, what is it that makes a problem so hard? Well, the first big clue lies in this huge, massive difference between two things: finding a solution from scratch versus just checking if a solution someone gives you is correct. Okay, let's make this super concrete with a simple example. If I ask you, hey, what's 3 times 5? The answer, 15, just pops into your head, right? It's almost instant. And for a computer, it's beyond trivial. We'd call this a super easy operation. But what if we flip that around? What if I ask you, hey, what 2 numbers multiply together to make 15? Now that takes a little more thought, doesn't it? You might have to try a couple of things in your head before you land on 3 and 5. It's just a little bit harder. And this is where that slight difficulty just completely explodes. When the numbers get really, really big, finding their factors becomes practically impossible. I mean, factoring a number like the one you're seeing here took the equivalent of 2,000 years of computer processing time. And you know what? This exact difficulty, that's the bedrock of almost all modern encryption. So here's the absolute crucial point. Finding the factors of that giant number is nearly impossible. But if I just gave you the 2 factors, you could whip out your phone, multiply them together in 2 seconds, and prove that they're correct. See that? There's this massive, incredible imbalance between finding and checking.
Okay, so this fundamental difference, this imbalance between solving and verifying, is exactly how computer scientists start to sort problems into different categories. So let's meet the main suspects in this whole mystery, these 2 families of problems known as P and NP. First up, we've got the class P. You can just think of these as the easy problems. The P stands for polynomial time, which is just a fancy way of saying that as the problem gets bigger, the time it takes to solve it grows in a nice, predictable, manageable way. You know, things like sorting a list or finding the shortest route on Google Maps.
Then we have the class NP. Now, NP stands for non-deterministic polynomial time, which I know is a total mouthful, but don't worry about the name. Just think of NP as the group of problems where even if finding a solution is really, really hard, checking a solution, if you're given one, is easy. That huge number factoring problem we talked about, that is a classic NP problem. And think about it for a second. This makes perfect sense, right? If a problem is easy to solve, then it's definitely easy to check. I mean, to check an answer, you could just solve it again yourself. So this means that the entire class of P problems fits really neatly inside that bigger circle of NP problems. Okay, but it gets even more interesting. Inside this big NP category, there's this really special group of problems called NP-complete. You can think of these as the absolute hardest of the hard problems in NP. But what's so wild is that they're all connected. They're like magically linked. If you could find a fast way to solve just one of them, you would suddenly have a master key that could solve all of them instantly.
So all these different clues we've been gathering, these incredibly hard problems, the fact that they're easy to check, these categories of P and NP, they all point toward one of the biggest, most profound, unsolved questions in all of math and computer science.
So back at the turn of the millennium, in the year 2000, the Clay Mathematics Institute did something pretty cool. They identified 7 of the absolute toughest, most important unsolved problems in mathematics, and they put a massive bounty on each one. A cool $1 million. That's what's waiting for the person who can definitively prove the answer to this next question. And the question is this: does P equal NP? Are all those problems that are easy to check also secretly easy to solve? Is our struggle with them just a failure of our own creativity? Or is there a real fundamental wall that separates P from NP forever? So this basically shows the two possible universes we could be living in. On the left, you have the world that most scientists believe is the real one. It's a world where P is just this small island in a vast ocean of NP problems, a world where some things are just fundamentally hard. But on the right, that's a much stranger universe. That's a world where P and NP are actually the exact same thing, a world where any problem you can check quickly can also be solved quickly. Okay, so you might be thinking, this is all very abstract, but why does this question matter so much? Well, the thing is, the answer changes pretty much everything. We're talking about computation, cybersecurity, even the nature of creativity itself. Look, if it turns out that P does equal NP, our world would change overnight. I mean, on one hand, it'd be incredible, a golden age. We could solve problems we can only dream of right now, like perfectly modeling proteins to cure diseases, optimizing global logistics, you name it. But on the other hand, it would be an absolute catastrophe for cybersecurity. Your online banking, secure messages, everything. It all relies on the fact that some problems are hard to solve. If P equals NP, all of that security, all that digital armor, just vanishes. Now, pretty much every computer scientist and mathematician will tell you they believe that P does not equal NP. It feels right, you know? It seems intuitive that creating a solution should be harder than just checking one. But here's the kicker. For now, that's just a really strongly held belief. It's not a proven mathematical certainty. So let's assume the experts are right. We're living in a world where P is not equal to NP. What does that mean for us, right here, right now? What do we do when we're faced with these impossibly hard problems? Well, it means we have to get creative. Since we can't solve these problems perfectly, we're forced to invent clever shortcuts, smart approximations, things we call heuristics. It's basically the art of finding a good enough answer when the perfect answer is completely out of reach. And honestly, this is where human ingenuity really gets to shine. And that kind of leaves us with a final, bigger thought, doesn't it? The P versus NP problem. It's not really just about computers and code. It's about drawing a line in the sand between brute force calculation and true creative insight. Maybe the real value in understanding what our machines can't do is that it helps us see and even celebrate the incredible, limitless power of what the human mind can do.